Hi, I'm Raf. I'll be telling you about quantum information elicitation. Before I begin, I wanted to mention that I'm not an expert in quantum information, and neither the paper nor this talk assume that you are either. So to begin, let's think about the classical information setting, specifically the scoring rule setting, where you have an agent with some private belief about some future outcome, a probabilistic belief, and you would like to ask this agent to report their belief, but they may report something other than their belief. And you would like to design a scoring rule that taking their report and some outcome that you eventually observe computes some score. And under the assumption that the agent will maximize their expected score and believe that the outcome will be drawn from their belief P, you would like to design S so that the agent will be incentivized to report their true belief. In the quantum setting, we now imagine that instead of a classical distribution, P, the agent instead has some belief about some quantum state. Let's call that rho. We'll get into the definitions later. And again, you ask the agent to report what they think this quantum state is. They may report some rho prime, which is different from their belief. And you would like to design, again, some score which takes their report, some observed outcome, and incentivizes them to be truthful. The catch, though, is that in the quantum setting, you cannot simply observe an outcome directly from the quantum mixed state. Instead, you first have to choose a measurement. And in the most general setting that one could imagine, the principal can choose this measurement as a function of the report rho prime. So once this measurement mu is decided upon, now with the measurement and the quantum mixed state, one has, again, a classical distribution which produces some outcome that the principal can observe and use that to score the report rho prime. And again, under the assumption that the agent is maximizing their expected score under this classical expected value given by the measurement, you want to design now a pair of a scoring function and a measurement function to, again, incentivize the agent to report truthfully. Now, of course, and we call such a pair a truthful quantum scoring rule. And just like in the classical setting, many questions come to mind as soon as you propose this definition. Do any truthful quantum scoring rules exist? What about characterizations? And in particular, we'll talk about restrictions on the measurement function, which are sort of quantumly interesting. I'd like to emphasize that while this setting is not meant to necessarily describe a principal-agent problem that's taking place in our economy currently, these questions, just like in the classical case, are absolutely fundamental to learning from quantum data, understanding the value of quantum information, and all sorts of decision theoretic problems. Okay, so for the talk, I'll give you a bit of the setting, a very brief introduction to quantum information that does not do it justice at all. Then we'll see our first quantum scoring rule, our first strictly truthful quantum scoring rule by reduction to the classical case using quantum tomography. Then we'll talk about some characterizations and restrictions on the measurement, and then very briefly a discussion of properties and statistics of the density matrix. Okay, so for background, let's start with the classical setting. So here you have a finite set of outcomes y. We'll let delta y be the simplex of probability distributions on y. And as we mentioned, the classical scoring rule is a function which takes a reported distribution over y, an observed outcome, and assigns some score. We write the expected score of a report p prime and the belief p in this way to be the expected score when the belief when the outcome is drawn from the belief P. And given this definition, we can succinctly write down what a proper scoring rule is. So that's one where telling the truth is optimal. And the score is strictly proper if a misreport is strictly worse. We'll make use of the log score, the classical scoring rule, which happens to be the one where the expected score function is the cross entropy between P prime and P. Okay, so quantum information. So for this talk, I think it's actually helpful if you're, somewhat familiar with quantum computation to kind of forget a little bit about the specific settings that arise in quantum computation, like qubits and even superposition and the very interesting quantum-y things that happen there. And instead, let's just think very abstractly about quantum states. We'll also ignore complex numbers for the talk and imagine that, our state space is the real vector space, even though it's actually the complex vector space in n dimensions. Okay, and just very abstractly, a quantum mixed state is a density matrix on X, which is an n by n symmetric positive semi-definite matrix with trace 1. So we'll just kind of take that as our definition and not really worry about where it's coming from, at least for the talk. A pure state is a mixed state whose density matrix rank is 1. So you could think of a quantum mixed state indeed as a mixture over pure states. So just as a simple example, here is a mixed state, which is a mixture of two pure states in the Hadamard and standard basis, if you're familiar, that gives us some non-trivial density matrix. Okay, so similarly, I won't be doing justice to what a measurement function is really, but a measurement, let's just say, is it's something that induces a linear map between density matrices and distributions over measurement outcomes. In particular, you could think of as a measurement as a collection of matrices, mu y, one for each y, and then the probability of observing outcome y from that measurement is just the element y's matrix product between mu y and rho. So as a simple example, again, let's take this density matrix we had before, and a measurement which is, we could think of a collection of 4 matrices for 4 possible outcomes. And if you compute the element y's inner products, you get some distribution over those 4 outcomes. Of course, there are some constraints on what these matrices can be that comprise a measurement. They have to be positive operators and sum to the identity matrix so that indeed you always get a valid probability distribution over the measurement outcomes. But for the talk, I think it suffices to just know that this is a linear map from density matrices to the simplex over outcomes from the measurement. Okay, so with those definitions, we can define a quantum score. So a quantum score is a pair of a scoring function, a measurement function which takes the reported density matrix and determines the measurement, and then the scoring function which takes the report and the outcome of the measurement and assigns some score. So just like the flow chart from before, the expected score given a report rho prime and the true state rho is just, well, first computing the measurement distribution and then sampling from that distribution, computing the expected value of the resulting score. Again, just like in the classical case, we say that a quantum scoring rule is truthful if reporting truthfully is optimal, and strictly truthful if misreporting is strictly suboptimal in terms of expected score. Okay, so with all of this background, let's see our first strictly truthful quantum score via reduction to the classical case using quantum tomography. So we'll need this definition. So we say that a measurement is tomographically complete if this linear map that it induces from density matrices to the probability simplex is injected. So in particular, if I have 2 distinct density matrices, then the distributions that this measurement induces over measurement outcomes will be distinct. So we'll map to two distinct distributions over the possible outcomes y. And if you think about it, then in some sense, if I just fix this measurement, the density matrix that's being reported is really just specifying indirectly some distribution over measurement outcomes. And the true belief is also mapping to some distribution over measurement outcomes. And so I can really just use any strictly proper scoring rule by first mapping to the simplex. So for example, here's what that looks like using the log scoring rule. So I take the report row prime, I compute the distribution over measurement outcomes, and I plug that into the log scoring rule. And because of injectivity and the strict properness of the log score, this will give me a strictly truthful quantum score. So I think what's interesting here now is, you may be satisfied, okay, there exists a strictly truthful quantum score, but I think, from a characterization point of view, it's interesting to ask whether this covers every possible quantum score that you could want to design. And, further we'll ask about restrictions on the possible measurements. So in terms of characterizations, the first thing that you might do is try to write down a general characterization of all possible quantum scores. And because there is some linearity going on between the density matrix, which is the belief, and the expected score, using similar templates from the information elicitation literature, you can write the expected score function as this linear approximation of some convex function. And so the characterization says every expected score function for a truthful quantum score must have this form, and the convex function is strict if and only if the quantum score is strictly truthful. So to kind of illustrate this characterization, let's plug in perhaps the most natural convex function in the quantum case, which is negative von Neumann entropy, the analog of Shannon entropy. And it turns out that in that case, there's a particularly cute form for the pair of measurement and scoring function that give rise to this particular convex function. And that is what I'll call the projective log score. So the idea is you interpret the report, which is a density matrix, as specifying a basis, which is its eigenbasis, and a distribution over outcomes, which are the eigenvalues. So because the density matrix is a positive operator and the trace is 1, the eigenvalues actually form the distribution over measurement outcomes, if indeed you measure in a basis. So the idea is to take this report and interpret it as suggesting a basis to measure in, and a classical distribution over the measurement outcomes. You measure in that basis, which is this set of n projection operators, and then you score the implied distribution over measurement outcomes using, in this case, log scoring rule. And amazingly, to me anyway, when I first thought about this does give you a strictly truthful quantum score. And I think what's interesting here is that, well, once a basis is fixed that is going to be measured in, it's clear, because we're using log scoring rule, that the resulting lambda prime will be the correct distribution over measurement outcomes. That is the optimal thing to do, just based on classical proper scoring rules. So what's interesting is that you don't have an incentive to misreport on the basis itself. You might think that perhaps measuring in a different basis will be optimal, but it turns out that if you measure in a different basis, you're sort of garbling the signal, increasing the entropy of the distribution, and therefore decreasing the expected score. So it's kind of not totally obvious that this would be strictly truthful. Sure enough, if you compute the expected score, you get negative von Neumann entropy. And I guess additionally surprising to me is that this scheme also works if you plug in some other strictly proper scoring rule. And doing so recovers many other, in fact, essentially all entropy functions that have been proposed in quantum information. They all have this same symmetry. Okay, so now let's talk about possible restrictions on the measurement. So for each restriction that we'll discuss, we'll ask sort of two questions. One is, can you design any strictly truthful quantum score with this restriction? And does it cover all truthful quantum scores? So is it expressive enough even with this restriction to get essentially anything that you would want to do? The first thing we can think about is fixed measurement scores. In fact, we already saw, because of the reduction to the classical case using quantum tomography, that we can fix a tomographically complete measurement and design a strictly truthful quantum score. And so you might ask, does this cover all possible quantum scores? And it turns out the answer is no. In particular, fixed measurement quantum scores cannot capture the projective log score that we just defined. The reason is somewhat subtle. It has to do with the fact that the projective log score can assign scores of -infinity on the boundary of the density matrices. Because if an event happens that you assign probability 0 to, then the score will be -infinity. And it turns out that there's no way to design a classical proper scoring rule that assigns a value of -infinity for a distribution which is in the relative interior of the probability simplex. And so this negative result kind of boils down to the fact that you can't map the boundary of the density matrices onto the boundary of the probability simplex using a linear method. Okay. Yeah, and as another way to think of this result is that if you want to capture the projective log score of von Neumann entropy, then the principal must have the measurement depend on the agent's report. Okay, so next we can think about measuring in a basis. And in fact, we know that there exists a truthful quantum score because the projective log score does measure in a basis, strictly truthful quantum score. And in fact, this will cover this restriction covers still all possible quantum, truthful quantum scores. And finally, I think it's interesting to ask, how many measurement outcomes do you need before you can design a truthful quantum score and to cover all truthful quantum scores? Because we have seen examples of measuring in the basis, you might wonder if n is the lowest that we can do. So a basis has n measurement outcomes when the dimension of the space is n. So we've, just by the row above, we know that you can, it suffices to have n, but it turns out you can get away with many fewer. So you only need 2 measurement outcomes to design a truthful quantum score. And even with 3, you cover all possible truthful quantum scores. And the 3 is essentially to accommodate the -infinity case. If you restrict to finite valued quantum scores, then 2 measurement outcomes suffice. Okay, so very briefly, let me tell you about properties of a density matrix. So here we're thinking of some property as a summary statistics that maps a density matrix to the correct value of those statistics. And a property is elicitable if there's some quantum score where now the report is a reported value of this statistic, and the expected score is maximized by reporting the correct value. I don't have a lot of time to tell you about the results here, but there are lots of properties you might think about, such as eigenvalues, eigenvectors, entropy of the quantum state, or some entanglement measure. It turns out of all of those, only eigenvectors are elicitable and the rest are not. And even worse, those that are not elicitable, using ideas from elicitation complexity, we can say that they're as hard to elicit essentially as the entire density matrix. So if you were interested in those quantities, even though they can be summarized in a small number of dimensions, you still essentially need to collect the entire density matrix to get the incentives right. Okay, so let me recap. We saw the setting of quantum scoring rules. We saw a reduction to the classical case using quantum tomography that gave us our first strictly truthful quantum score. Then we saw a bunch of characterizations that reflect similar characterizations in other areas of information elicitation. And in particular, with restrictions on the measurement, we saw that not all restrictions are expressive enough to cover everything. And finally, we briefly discussed properties like entropy and eigenvalues. I think there are many directions that are interesting to think about, such as elaborations, more complex settings in the machine learning of quantum information. And the paper also discusses restrictions to pure states and a sort of inverse problem where the agent is asked to prepare a quantum state. And looking further out, while not so practically interesting right now, I think it's interesting to think about prediction markets and wagering mechanisms, other elicitation mechanisms in the quantum setting, which may have other interesting applications. Thanks so much for listening.